Again, we're going to only 2 weeks, so I'm jumping from topic to topic, just give you some highlights. So this is like a topic. This is what Shannon essentially and Hamming also all our paper initiated. So what are the reporting codes? Well, just to give you the quick sketch here. Essentially, you have two parties. They're also always called Alice and Bob. And Alice wants to send a message to Bob, and maybe she wants to send the message in English or in bits or whatever. So this is the alphabet that she's using. And she wants to send a K symbol, say K bits name to Bob. But the problem is that sending the message could, because of the faulty kind of line of communication, the bits things could happen. So for example, symbols could be flipped. Oh, things can happen. Be erased. It's simple. Bits or symbols can be flipped. Not all symbols will arrive safely, but they will arrive in the same order, but just maybe not safely. And then therefore Bob will not be able to recover. So the idea is to overcome this. The idea is to just before sending M, that's the wrong idea, is to kind of add redundancy to the code to the message. So apply some function, which inevitably is going to produce more symbols because you want to add some redundancy, such that when you send C of M, even if not C of M appeared on the other side, but not too many of the symbols will flip or change, then it will be possible for Bob to recover M from the noisy version. So it's just they want to add more redundancy so to account for the errors. So really, for us, that's the story, but I don't really care. For us, the story that for us, the definition of a code is essentially any function from over an alphabet sigma, 0, 1 if you want, or sigma indicate to sigma again. Any function is a code, but you want the code to be good. You want to be able to use it for the communication. So you want it to have what's called the distance. So what's the distance of the code? The distance of the code is really just the distance, like the Hamming distance between every 2 points in the image. So we take any 2 messages. So this is the whole of the messages. And you look at C of X and C of Y, and you look at the Hamming distance between them. Where I remind you that the Hamming distance of 2 strings is just the number of indices in which they disagree. This is just the number of i's in n, number of indices in which they disagree. But this is not the same. There are 2 different distances. This is between like strings, and this is the distance of 7. What do you want from this thing? So you want the distance to be large, because you want to make sure that different messages translate. So after you encode them, they kind of get far enough from each other. Then they have many disagreements, so that if I change C of an X at some of the indices, it will still be close to C of X compared to the C of the other Y's, because the other are very far apart. Right? So I'm thinking of if this is sigma to the n, then maybe this is C of X, this is C of Y, and then kind of iterating on all of them. Then 2 points that are close is a problem. Because say for example the distance is 1, which means that there are exactly 1 index which you disagree. Then an adversary can easily fool you, because he can, if you send the message corresponding to this, that's called the code word, when I can change 1 index, Bob will get that one, and then you will infer that actually another message is sent, right? So you really want things to be far apart. And actually, if the distance, let's call it d, if the distance is d, then as long as less than d over 2 indices are corrupted, then you will be able to recover the message, right? Because if you can think of it as a little kind of ball here, if the radius of radius d over 2, or maybe d over 2 minus 1 or something, but if the distance is, I mean, this is what you send, but if you made less than d over 2 minus 1 changes, then you are still within this ball, and the balls surrounding different code words are non-intersecting because of the distance. So this means that whatever you got, at this information theoretically, whatever Bob got here, you should be able to, maybe take a lot of time, but you should be able to infer what this is.
What about the instance in which you can collect the word, you don't know that it's a corrupt message?
Right.
Detection.
Right. Good. So you can also do that for slightly larger things. But yeah. But I say I only care about, I actually don't care about in code. I care about. I don't care about error correction or detection or recovery or local error correction, etc. I just want to give like the combinatorial architecture. But like you can and do give courses only about that, and then this takes an hour. But just to give you the idea, I mean, you want essentially a function that spreads finger. The reason why you would want it, I mean, the original reason was simplification. It turned out to have many more applications. It's pseudo problem. But that's the underlying story. So you want a function like that has good distance. On the other hand, you don't want n to be too large compared to k because that corresponds to the amount of redundancy. Like if you want to, if n is 2k, then it means that for every 2 symbols you send, you only send 1 symbol of information. So that, in terms of communication, that's waste. So you want the waste to be minimized and still the distance to be large. Like you don't want, I mean, depending how you think about it, but if you have k in mind, you don't want to embed these symbols, sigma to the k, in a sigma to the n for n, which is too large, but you do want them to be distant from each other. So it's kind of contradicting properties, right? You have assumed they will kind of, at the end of the day, they will be closer to each other. So the way we formalize it is as follows. So it's actually, before doing that, let's denote by delta or delta of the code. Code will always be clear from the context. Delta is the distance, but let's divide it by n, so it will be a number in 0, 1, just to normalize it. And let's denote the, so this is called the relative distance. And the left code is the whole, just k over. Just a way of measuring, you might have thought of n minus k or something. All the same, essentially. It's really the how much information you have in a symbol that is sent. And because if n is 2k, for example, you have half, every symbol that was sent has contained like 1/2 of information, half a symbol. And this is also, of course, another in 0, 1. I mean, you're not going to take n smaller than k, then there will be a collision. It's worse than just sending the message. So you have these two numbers, delta and rho. This determines how condensed are the code words. The code words are just the image of C. And this codes captures the distance that you want between them in the worst case. And their competitive parameters and are in 0, 1. So the question is, can you make both of them 1? And you can. It just doesn't make sense, but how much can you make them close to 1? So first of all, the bad news is that, well, you can't make them both close to 1 in that sense. Just add a little bit here. So incorrect the way I said it, but it doesn't matter. Okay. So you won't see that. Don't see the plus one over there. But essentially, rho plus delta is at most one. So both of them are between 0 and 1. But one is good, it's bad. But you can't make them both close to 1. So if you give them equal footing, for example, that's one example. So so they are both are as important to you as other. And the best you can do is get them. You cannot do better than that. We'll see that you can do that. You can't do better than that. The proof is trivial. And I didn't understand for a while. Maybe I shouldn't say it, but it's kind of a video. How does it relate to a singleton, like a set theoretic singleton? And then it told me that it's a person, it's a name. So, okay, there's nothing singleton about it. So the proof is like essentially trivial is a pigeonhole principle. You're looking at so take a code, any code, right? And look at the maybe k plus 1 coordinates. Say any of the k plus 1 coordinates, say the first one. Then, because a minus better, then because you're sending sigma to the k things there, and what you looking at that, you're really just projecting sigma to the n to the first k minus 1 coordinate. With the pigeonhole principle, there will be collisions. These two code words will have the same projection, only sigma to the k minus 1 projections. So this means there are two code words that will agree here. And so the distance of these code words, in particular, the distance of the code, will come from here. This is the only place in which they can disagree. But here you have an n minus k minus k plus 1 entries. So it means that the distance is at most that. Because the distance of these two code words in particular is at most this thing. We denote the distance by d when we have this inequality. And then, I know it's a bit fast, but it's written in the notes also. When just moving to the other side and dividing by n, see it's plus 1 over n. Cannot avoid. Yes.
Why did you choose k minus 1? Why not k?
Because when they may, I want to enforce collision. So I'm sending sigma to the k. When I say sigma to the k, I mean the size of sides. Sigma to the k things. Sigma to the k things to sigma to the n. So they are going to be spread around. But if I'm looking only at the first k minus 1 coordinates, there are more things I'm sending than things to be.
Okay, so you're assuming that the k bits is the same.
No. I was just saying that if any function like that is not injective, there will be a collision because this set is larger than. Yes. It's like an overkill event. And therefore, C projected to the first k minus 1 coordinate, that function, there will be two inputs. It will map to the same string. So now if I'm looking at the entire C, then I know that, okay, here they are the same. So I say x and y. C of x and C of y agree here, so the distance will come only from here. Because, okay, so what I'm saying is that this is non-injective. There is a non-trivial here. Except theoretic, there are two x and y's that go to the same place. So C of x projected to the first k minus 1 coordinate, you can find. I mean, I don't know if you can find, but there are things such that this holds. And now I'm not just looking at the projection, I'm looking at the entire C of x and C of y, and I say, okay, they agree here. So the distance, the number of disagreements, is only coming from these indices. But there are at most there are n minus k plus 1 indices here. So the distance be at most n minus k. Sorry, I should do it more slowly. Particularly, I'm not sure I can decode the proof from the board now. I'm not sure exactly what. But the notes actually are very nice. But that's a good excuse. So that's the bad news. by the way, in general, just you have this axis of things. You have a problem, and you have the lower bound. This is the bad news, and you have what the probabilistic method tells you. It's not exactly the same necessarily. It's definitely larger.
Yeah.
And then there is what like as a community, as people, like socially dependent, like what we know how to do explicitly. So usually the situation is that this is larger than that. It's not obvious. Yeah, we're talking about stuff. Sometimes, amazingly, but very rarely, structure is kind of weirdly. Structure is actually, you can use structure to beat the probability. It's very rare.
This method is random. That would be.
Yeah, so if you have the problem, add two numbers, you shouldn't use the probability. But if you have a problem which is not structured, like essentially this code thing, right? The best thing to do, I mean, but the best thing to do, like, first thing you should think, the best thing to do is to force these points at random in sigma to the end. You don't need distance r because that's there's all. I think should be fine. And actually, we'll say exactly to what extent. But it turns out that even in this example, when sigma is slightly large, it's 49, you can actually use structure. You can actually use the structure to get something which is better than just throwing the things up. Which is surprising because there are like 3 examples. That's like surprising. Usually, I mean, it could be the case that for many problems you can do something better than the probabilistic method. You never managed to do it. But what I want to highlight here is that this is probably this is hard, usually hard, because proving a low bound, this was it actually. But proving a low bound usually means you really need to understand the problem. Like, doing an upper bound means, that you can give some of yourself to the problem. You know like algebraic geometry, so you manage to use that to do something. It's not only about the problem; it's also about you, like how you think. So you're here, and maybe I'm here. Here. But this has nothing to do with us. Right? This is I mean, you can always get I guess the knowledge is kind of bad because you can also get terrible low bounds. But to get a good low bound, well, I guess it's a bad idea. Usually low bounds are harder to get, but not here. Which is essentially. And this is very easy almost always. And that's cool. Right? The fact that you can almost immediately get that. Okay, so let's do that. So we just did a lower bound. So this is the Singleton bound in the operating cost case. What about the probabilistic method? What does it give us? So do you know the name of these? The two names. Yes, but like people names. Gilbert-Varshamov. These are 2 different people, and also, but one of them is what I'm going to say for general codes, and the second one for linear. Say what is our. Doesn't matter now. So, no more with us. So I think it was like 52 and 57. I'm not sure. Plus, so they proved that I'm going to slightly massage it to make it similar to that, but it's something slightly stronger. But they proved that for any delta n row that you want, there exists a code. So let's see again. With this distance of this parameter, with this way, with this relative distance of like row, Assuming, but here there's something missing. Assuming delta plus rho is most, right? I mean, something has to bound your expectations. And then there is some constant here. This is a universal constant, which I don't remember. So Singleton tells you cannot get one. You can actually get one, but you cannot do better than that. And well, they said, well, you know, so here I put them on equal footings, but on equal footings. But once the alphabet size is sufficiently large, you can get close to one, and the rate in which, so this gap deteriorates with the inverse logarithmic of the alphabet size. So the larger alphabet size, the easier. You can actually, so when looking at that, you don't know if you can get something from binary. But you can actually get. So they also tell you that there is a binary code with rho, and I mean they also consider the case where this is a 0, 1, but it's not close to. Then it's slightly different. What I'm slightly cheating here is that they actually gave us something, some stronger. So it's not delta plus rho, it's delta plus the entropy of it. And this in particular implies that. So slightly cheating on the safe side, but this is what you can infer from that. One thing you can infer is that once the alphabet is large enough, you can get the distance and the range after this guy. And the way you prove this, I'm not going to prove it, it's actually easy. You just you take a quad at random. You just take sigma to the k elements here, uniformly independent at random, and you can just argue about the distance between them, take the unit power. Very easy. Maybe we'll do the next step. Okay. What about constructions? That's now the interesting one. So, what's the mother of all codes? If you know codes, there's one answer. No, Hemming code is like the Reed-Muller. That's something.
Just to clarify, because I see in the notes that you wrote, like the influencing in the other direction. Sound that both is like setting the notes as bigger or equal to 1.
Right. Maybe I said that there is one such that this holds. You can either say assuming this or such that that.
Okay.
Right. So same thing. Yeah. That's the right direction. There is a restriction. So in the notes, the way under the restriction, that's a restriction. Doing a lot of in the other way, which even if that's larger than that, then you can. Okay, so with someone is like I think the first example. So this again has 2 people. There's also one person that's called lead someone. So again, I thought with magician, one magician. So this is our real example. I'm going to show it actually extensively. We're going to get into the detail, but it's an example of a construction that uses polynomials over finite. And when you see this problem, I don't think that's what you're going to do usually. Like when you look at this question, you know, think of sigma 0, 1, and then you send k bits to n bits such that, you know, whatever, they are distant apart. I think that you're actually going to try to do it. Take, you know, maybe the first couple of bits and take the parity or something and put it and like that. And like play with bits or something. And it's not how it works. What I'm going to show now is like it's a matter of all codes. Oh, but it's actually the matter of all techniques. Using polynomial over finite fields, is the only way. Two ways. It's one of the two ways we know how to. It's not like it's a weird construction. It's essentially the only case. Maybe it's weird. It's the only. The other one is from expander. But what I'm going to show now is actually the basis of many of the things we do. Definitely important. With no polynomials or finite fields, we could end up with polynomials. That's how it works. So let me tell you about internal codes. So we want to construct a code with good parameters. Okay? So the first thing I'm going to do is I'm going to give some structure to the alphabet. It doesn't have to have structure, but I'm going to imagine it as structure. I'm going to take it to be a finite field. So I'm going to construct a code for the someone for finite field of size q. I mean, I'm going to assume that sigma is a prime power size, so that I have a finite field of that size. And I'm going to show you how to construct this code. 20 parameter scalar, essentially. So before I'm describing the code, I want to interpret the message differently. So currently the message is, you can write it maybe as M0, 1, this is a message, MK minus 1, and I left step from 0. So that's a message, right? That's on two sides. Still you have an unstructured string, and I want to interpret it differently. Think about it differently. So I'm going to define polynomial, one variable. So it's a univariate polynomial, Q, and for every message you have a different polynomial. And the polynomial is maybe what you would expect, given that I told you I'm going to do it. What's going to be? Okay. What this will be? Good. So you said the two. Good. So you can either take the coefficients or the roots. You can choose. Take a pick. So I'm going to do the coefficients. Even though I'm actually a fan of the other two. So that's usually how it's. Oh, love it. So you can, we did nothing. There is no computation here. We're just kind of giving structure to the message, also to the alphabet. And then, okay, so we just played around. We did nothing. We didn't encode anything. And so now, given this interpretation of the message, we are going to define the output. So we take some endpoints near Q, distinct points, which immediately implies that Q is at least n, but I want to take distinct points. I'm going to call them P1 up to Pn. And then the encoding is as follows. So the code takes the message, and it thinks of a polynomial, thinks of it as a polynomial, and what it outputs at the different indices is the evaluation of these polynomials on these points.
Only in the scalar, the number?
These are elements of a finite field. So finite fields, right? So if Q is a prime, then a finite field of a prime size is really just a number between 0 and P minus 1, is a prime P, and then addition and multiplication is modulo P. So you can think of it like that. Just you add and multiply modulo P.
So it's a number.
It's a number, but everything between 0 and P minus 1. But I would say that fields that are not primes, there are fields that are not primes, that are prime powers, and only fields that are prime powers exist. All of them exist. These behave more complicated, but you don't need that for this or for anything. So you can take of Q as a prime. Well, except for the example I'm going to give later, but it's just an example. Okay, so let's just see. So this is an element of FQ, and this is an element of FQ, so it all makes sense. It's FQ to the n. And that's in terms of types, everything is okay. Also, if you believe it that you can work with finite fields, it's explicit. You can add and multiply. It's very explicit. It's actually kind of depend on the finite field. It's very explicit. What are we missing? What would you do now?
Okay.
Distance, right? The directive K over N, we want to understand the distance. Distance analysis. Okay, so what should we do, right? We should take two different messages, which we should think of two different polynomials. And ask how many, right? So maybe so there's this one, and maybe there's another one. So maybe there's F1, N. So this is one code word. And another one would be F of some M prime, right? One. So this is when you encode M prime, and this is when you encode M. And the distance is in how many indices they disagree. And Fm and Fm prime could be any 2-degree at most k polynomial, k-1 polynomials. So really, I can, and maybe we should just do it. Instead of asking how many points they disagree, I can just ask in how many points. So if we just write it like, just spell it out. So I can ask instead of that, if I look at kind of subtract the two vectors pointwise, then I can ask in how many points here are 0. But this is a general degree k-1 polynomial. So it's kind of essentially the same as asking in how many points can a degree k-1 polynomial can be 0. No, the answer. It's a non-zero polynomial, by the way, because these are distinct. So in how many points how many zeros does the polynomial of degree k-1 have? K-1 most, right? Right. So it has a name. It's called the fundamental theorem of algebra. It's actually has a very nice history. Maybe later. So by the fundamental theorem of algebra, not sure they call it that. The number of zeros in the lateral vector, which is the number of agreements between the most k-1, that's the degree of the polynomial. We're keeping this -1 because it's going to be the plus one of the name. So the number of disagreements, which the coming distance, is at least n minus. The degree k-1 polynomial because you start from 0. It's already erased. From here I can see it here. Like the ball will move. But degree k-1 polynomial, you start from 0 up to okay, so this means that the distance, so that's the distance. This means that the distance is distance minus k plus 1, or distance k distance minus 1. Or if you want, you can divide by n to get that. But that's what Singleton can do. It's possible to go. So now you actually attain it. And so again, so we interpret the message as a polynomial, and the code was to evaluate the polynomial at different points. When the analysis, in the distance analysis, the question of how many points of agreements are there, what's the Hamming distance, kind of translated to the question about zeros of polynomials. So the two messages are evaluating the polynomial at different points, and the same points at the same point. And when an agreement corresponds to a zero of that polynomial, and that polynomial, which is a non-zero polynomial, here was k-1, it cannot have too many zeros. was k minus 1, so that is n minus 1. 9 zeros. So the distance, that's all for every two messages. I'm not sure if it's like weird. Initially, when you see it, it's weird. It's like it comes from nowhere. You want to construct a code, you think of bits, and then I throw this idea of polynomials, and then somehow you write the fundamental theory of algebra there, and it's weird. But you see, you need structure. You need to be able to say something, unlike the probability method that says nothing. Actually, look at everything combined. It doesn't look at a point in the probability space. It looks at everything together. If you look at one point, you better understand how it behaves, right? So you need structure. And what structure do we have? We have like polynomials. What do we have? Groups, linear algebra, everything like in the first semester. So that's it. So it's not weird. It's actually inevitable that as humans we are going to use things that humans know. That's how it works. Okay, that's a great code. The distance radius is like optimal. There's one problem with it. I mean, it's a good code. I mean, still, there is one problem with it, and that's that Q is at least n. I mean, it doesn't make much sense. I mean, depending on what you do, but if you consider the initial story that we have, it doesn't make sense that Q is not keep there. But I want to say the book is very long. And you're telling me that my argument should be at least a good step. And you say 26, 50 letters. I'm not going to. I want to send books that are longer. It doesn't make sense. So, like, one way to do it is to cut it into chunks. So, the question remains: Can you get like a good code without this restriction? So, any questions about that before we move forward? Was this class? So let's do the first attempt at the constructing codes in which Q is smaller than n. I just want to exemplify the idea that go into instructions. These are just case studies. Don't care about the Reed-Muller code. Care about it, but I don't care about it for this lecture. Just using it as an example. Okay, so there is a natural idea. I mean, you want more points. Here you use. I mean, here the number of points is coupled with the field size, and that's bad. So you want more points with the same field size. So what should you do? Like, it's one obvious thing.
Well, maybe take more variables.
Exactly. Take more variables. Exactly. So what will happen if you take a code that we will think of his messages as say bivariate, two variables. I mean, something should happen. Right? So let's see. So again, so we are going to construct a code. Now it's Reed-Muller. I'm pretty sure it's the same way they never changed. So again, it's going to be a code about finding fields. We're going to have polynomials and so forth. But now I'm going to think of the message as a polynomial in two variables. And I'm going to evaluate this polynomial at a plane other than in line. It's a good idea because here you have Q squared points rather than Q. So in what will come in a second, this condition Q is at least n will become Q squared is at least. We'll see that in a second.
You necessarily need like to it's like a same field for just like you and me like outside the product.
Yeah, you can do some about it. I'm not sure. Let's see if that makes sense. Let's talk about it. Let's for now. I'm just going. we'll see that in a second, but in a second, that constraint will be relaxed to that one. So anyhow, I'm going to interpret it as a the two values, let me just try to see that way. So I'm actually, I don't even have this step where I take a message and think of it as a polynomial. I mean, the messages are the polynomials. So I'm asking myself, how many polynomials do I have? The d at most k. We can do k minus 1 as before, but let's do k. So, and when I say polynomials, I mean polynomials in two variables. And when I say degree, I mean total degree, the sum is. So polynomial might look like this. For any message, let me just argue. So say these are the messages symbol. I'm not calling it M0 up to M k minus 1, I'm calling it Mij because it's easier that way. Ij are going to be from 0 up to D, let's call it T for the degree. Okay, so bear with me for a second. So bear with me in the sense that I don't know what T is for a second, but I'm going to think of my message as being indexed using two indices, really, Mij, like ordered indices. And I want to have, I want to use this message symbol as a coefficient of all, x to the I, y to the j, and where I plus j is the most. Where I plus j is the most. So that's it. Total degree is the most. The other one is also good, but found in the individual rather than total degree is. Right, no, so good. So what I'm going to do now is to relate T and K. Right, so let's do that for a second. So I know that the number of pairs Ij is K. So I want K to be equal, or smaller actually, if it doesn't really matter. It's equal to how many solutions do you have to this thing? So I think it's T plus 1 plus 2. Now if you be down with me, then you know how to do it. Right, you have, let me do it for a second. So you can do I plus j plus a dummy, something is a dummy, equals t, and then you have like 2 sticks. So it's a t plus 2 minus 1. You have 2 sticks, so it's 2, sorry. And you need to choose what the 2 sticks will be. Now you can trust me that this is the number. So the number of solutions to that is the number of solutions to that. And this is easy because there's 2 sticks out of the 3. Anyway, you should think of it as this code. T plus 2. No, there are T, but there are T things you put plus 2 sticks. Right, so you put 2 things. I do not. The sticks came from no, right? What I kind of did here, sorry, what I did here was just calculating, and I had sticks in mind, I just projected it at you, but how many, so given T, how many pairs Ij do you have inside this?
5. What equation?
This. So how many Ij's from 0 up to infinity you have, such that I plus j is most.
Okay.
And then the way I remember how to do it is. But
M I to J what?
so good. So M is the message. In Reed-Solomon, M was in FQ to the K. And now it's in, oh my God. Now it's in, also in, there are lots of K symbols, but I'm going to index them differently, like Mij rather than Ni, because I want to use them as a coefficient of a bivariate. It makes sense. So the number of pairs, so the indices are that. All Ij's satisfying this. These are the number, and once this is K, I can go back and forth between the 50 and 1.
So take the method and put it in matrix, and then
Yes, exactly.
Okay.
But only like in the lower diagonal or something. when I plus j equals t. Okay. Really nothing happened there. I just took a message and I just indexed it differently because for the purpose of what I'm going to have, it's nicer to have like a double index, but a ordered one, right? So first index and second index. And I want to kind of squeeze k indices to that way of indexing thing. So I just call this for a second, I call this bound t, and I figure out the relation between k and t. So I can squeeze k symbols. Makes sense, it's going to be a square root or something. Makes sense. That's what it is. This two is not important, this two is important. Okay. So just to recap, we are defining the Reed-Muller code. It's a code that think of the message as a bivariate polynomial, where the total degree is at most t, and t is like a parameter, but it's actually fixed given k, because you want to squeeze all k possible symbols here. So think of k should be actually exactly that, but think of it as t squared over 2, it doesn't really matter. But I keep over 2, right? That doesn't matter. The constant that matters and constant doesn't. That matters because it's like divided by not added to. Okay. That's a code. Every function is. Sorry, what's the code? So the Reed-Muller given a message, it's the same thing as the Reed-Solomon, it just evaluates the message at 10 points, but now the points are living in 2 dimensions. The point is like something here. Then let's just evaluate it in the entire. Okay. Let's assume that k squared is. I mean, we are really trying to minimize q, so let's assume k squared is. No, it's 10. So you're referring to this level too?
No, so then the two in they can.
No, so okay, good. So I'm going to take a field. So I'm going to take a field in which this is an equality. So q is square root of n, and therefore you have n, which is q squared. So the code is for. So the code is for. That okay?
So, did we choose like k to be 2 or?
No, so k. So you're given k. Okay, so sorry. Let me just. You're given k and n and q, but let's immediately take n to be equal to q squared. This will be easier because I want q to be the lowest possible, and that's the lowest possible. So you're given n and k. Q is therefore square root n. And now k is k, but this polynomial is of degree at most t, and I'm just saying that t and k are related by that.
Okay.
I care about the degree because in the distance analysis now it's going to come in. So this is just a correct. So every message is mapped to, right? So every bivariate polynomial, you give me a message, you evaluate it here and here and here, and you get different elements in the queue. So distance analysis. So the same question as before. If you take 2 such polynomials, or maybe 1 such polynomial and compare it to 0, difference. How many zeros can it have? How many zeros a bivariate polynomial can have? You know what's the idea? Oh, we'll circle back to that. That's like higher. No, that's actually used to, no, I don't know, maybe, but the Schwarz-Zipf. Good, it was this kind of thing. And I'm writing it like fast, but I'm not sure how to spell it. And actually, it's kind of one of these lemmas. Again, these are 2 people, and these are not the first 2 people to discover it. There is the lingo and someone else. But I don't know. Everyone calls it Schwarz-Zipf lemma. But it's an easy lemma. I wouldn't mind people taking this lemma. So this lemma says it's kind of easy, naive, but tight. So that's all we can do. Generalization of the fundamental theorem of algebra, and it uses that to two variables, any number. So what it says is that by degree I mean total, like we have, where the degree of a monomial is the sum of degrees, and the degree of a polynomial is the maximum. So a total degree D, or let's call it T here, polynomial, like ours, the finite field, has at most, any good guess? I mean, how many zeros? I mean, if it was in one variable, it could have T. So it's like a T over Q fraction. So it remains like a fraction. At most, TQ zeros. So out of the Q squared. So it's still a Q fraction. You can always get that by just knowing y. Having a polynomial of only x, if you have T zeros, and it knows y. So regardless of y, you have. You can do better than. Well, you said the zoo, and it does something better than that in some sense, but like in the general case of that, you can do better than that. When you value the polynomial on the entire plane, that's the best. Okay, so that's it follows by a simple, not completely trivial induction to the fundamental theorem of algebra. It's not completely trivial, but it's the first thing you do after the first thing you did take. The first thing before. Okay, so what does it tell us about our case? Well, just says that the number of zeros is most P, Q, which is this when you can get T and Q out. Right, so and again, the number of zeros corresponds to the number of agreements. Exactly. So the distance is n, which is by the way Q squared, let's remember, minus TQ. The distance, like not normal, just the distance. This. You can also obtain the distance is this thing, right? N minus, because this is number of agreements, which is right Q minus T if you want. Okay, and okay, but we care about the rate distance, so let's look at the rate first. So what's the rate? The rate, now just like shuffling things around, is K over N. That's always the case. If these are K and N to think about. K in our case is P squared over 2, and N is Q squared. Which is this thing. Now the relative distance can be coming from there, but also normally, so the relative distance I should divide by Q squared, by N. The first Q will go this Q, and the second Q will this go away here. So this is 1 minus T over Q. Okay, so the best way I like to write it is that the rate is half T over Q, so it's 1 minus delta. So just T over Q appears here. You stare at it and you're happy. You're happy because you get a code, right? For every row in delta. So for any delta you can play with it. But for any row in delta that satisfies that, or there's always like that. You can do worse if you want. As long as row is not too large, you're happy. But what's the there's one traveling thing here. First order thing that travels is what? The half. It means you can't do better than rate 1/2. It's like whatever the delta is between 0 and 1, you can't do better. That was a problem for a while, but at least what we know. Well, you know that you got a code, or it has this disadvantage, but you know that Q is square root. So good and bad, right? So it's not that terrible. I mean, the half is annoying, but the alphabet is lower. And if you are thinking of, how can you generalize it to something better here?
The root is the line.
Exactly, higher dimensions, right? So you can take like polynomials in, say, m variables. Maybe that's a good idea. I don't want to do it here, it's not so terrible. But obviously, then what will happen is that n is going to be q to the m variables. So there is an m. R. Okay. But then you can ask, this half, what this half is like an instantiation of something that happens in the R. So what is it? And it turns out that it's most one of the R token. And then I'm not sure exactly what happens here. Let me just write it. Because I don't care what happens here. This already is a deal breaker, but I think that's what happens. So Reed-Muller is like not out the gate. But it's a good idea. It's not, it allows you to decrease the alphabet size, score root and then O, but then you pay in rate so much that it doesn't. If you want to get to a constant alphabet size, that would be have to do log n, and one of the log n is on the one at the end. So I think it's a good code. It's also better than Reed-Solomon in many senses. Not just, when you do coding theory, you don't just care about distance and rate. You also care about other things. And for example, Reed-Muller has this cool property, understatement, that it's what's called just for fun. Let me tell you, it's a locally decodable. So what does that mean? It means that say Bob just wants to obtain the ith symbol of the message. You got the entire code word, but it doesn't care. It's like a phone directory or something. Just wants something. So of course he can decode the entire message and then look at the IFMP, but you want something more efficient. Something that's just able to look at only a few entries code and figure out which sounds weird because it must imply that there is some structure. So if you're allowed to be able to do that, it means that there are a few entries that correlate with the message. It's something structured. On the other hand, you want rate and distance, so there is randomness. So there is a randomness structure there. But Reed-Muller allows you to do that. And the idea is the following. So given the code word, and then pointing at that because that's the code word, right? You see a polynomial evaluated at different points in the plane. You don't want to read all of them, you just want to read a few, but that's the polynomial that you see. And there is a way to read only square root of n symbols and figure out the thing you want, rather than read the whole n. And you can improve that square root of n. So the idea is to just take a random line that goes through the points that you are interested in, a random line in direction, FQ. You should feel comfortable with lines in FQ. It's kind of fluid because they don't look like lines. They look like. But when you don't draw them, just think of how you should. If you are an FQ creature, it would look like a line. And what you can really show is that because the line is random, the fraction of errors on it is roughly the fraction of total error, right? Because it's a random line. It didn't commit to a specific line. So the adversary that can put the errors didn't put errors on top of it. So you're really in a situation now when you're looking at your bivariate polynomial, but only on the line, projected on the line, and this is really just a univariate. And it's of degree at most T, when you project a degree, total degree T polynomial, you get a univariate degree T polynomial, most. And you're really in the Reed-Solomon. So you use Reed-Solomon decoding to be able to find that. So you only need to read square root of functions. Okay, just
Can you explain again what is this line?
right. So you choose a line. So you want to figure out what's the code will be, what's the entries that appears here. So you choose a line that goes through that point at random. By line I mean like literally parameterizing a line. Like if this point is like, or if this point is like, let me just put it here. If you want to read the point x0, y0, so you look at the line which is goes through that point. Maybe you can write it like this is not the same as this one. So you choose two elements, so a point. This is the slope. A point at random, an FQ. Each of them is an FQ element. A point at random in the plane. And you see this line, so T is the parameter that runs from 0 up to Q minus of FQ. So when T is 1, you get this point, which means that you go for the point. In general, you interpolate. So this is a line. This is kind of the slope in a sense. It's related to the slope, but you choose this at random, which has the effect of taking a line that goes through this point at random. And going into the form.
Just that pinpoint with polynomial.
No. Okay, see what you're saying. These are not the points that are the message. This is the message. This is the code node. So you have a message, and you evaluate the polynomial corresponding to the message on the plane. Right. So in every entry here, you're going to have an FQ element, which is the evaluation of the polynomial at that point. Right. So if you think of it as height, it goes to it's FQ. So that's right. And then, given that, so looking at the plane, you can take a random line and then look what the polynomial did on that line. It's really a Reed-Solomon polynomial. It's not something I call it. I just mentioned. It's really cool. Okay, so let's improve the half, just for fun. Usually don't do that, but let's do that. Because I want to show you that it goes beyond. Okay? So how can you improve the half? Now that doesn't it actually took a lot of time to improve the half. It's only like 10 years ago. I mean, people knew how to construct codes that are not Reed-Muller in better ways. But they didn't know how to but they liked Reed-Muller because it has other properties. So they wanted to have a Reed-Muller-like code, also evaluating polynomials and stuff like that. It still has better range, right? But it doesn't. So you need to pick this thing. And the idea was, and it sounds weird, to add the evaluation also of the derivative. So let's see, in here. Yeah, just erase the thing I want to. Stupid. Okay, so what's the idea? The idea is we are going to again think of the message as a polynomial, but then we are not going to evaluate the polynomial alone at the point. We are going to evaluate the polynomial together with its two-directional derivatives, which is defined like formally, just derived like you would. Okay, so we are going to define, these are called multiplicity codes. Because as you see in the analysis, you are going to learn about not only about the zeros, but also on the multiplicity. But multiplicity code, so it's kind of the same thing. So we are going to have the total degree T polynomials in two variables as inputs, messages. But now we are going to evaluate the message, the polynomial corresponding to the message, as long as together with the derivatives. So you're going to output actually 3 symbols per entry. So here you output 1 FQ element, you're going to output 3 now, which sounds like terrible in terms of rate, because you just started with a 1/3 loss. It's very counterintuitive. Already at 6, because it was a half there and here. But we'll see. So, right, so here I'm kind of changing the model a little bit. The way I defined code was from sigma to k to sigma to n. Here I'm using different sigmas. It makes complete sense. It's okay, people do that. But then the rate, I mean, should be like how many information is here divided by how many information is here. So it's going to be k over 3n. Okay, so what's the code? So the code is going to take the message. And so it's going, before it was, I'm evaluating the polynomial at a point. These are the fixed points in the plane. But now I'm going to output a triple per point. So this and the directional derivative P1 and the directional derivative Y, which is exactly how you think they are defined. Just there. So this is for P1, and you have another one for P2 all the way up to Pn. This is one symbol, right? Just to make sure the parentheses are one FQ cubed symbol. It's a little bit of cheating to increase the alphabet size, by the way. Because, for example, there is a very simple code. They just take the message to a symbol, which is the message. Distance is 1, X is amazing, but the alphabet size is like huge. So that's not fair. That's like a more modest, kind of moderate and unfairness, and you can actually tweak it back. There is a way called concatenation in which you can actually, if you didn't do too much harm, you can balance it back, and it doesn't change much about, the rate and distance. So it's not such a big deal. But I just should know that it is somewhat a little bit of a cheat. You can't increase the alphabet size. You send a bit, I get like 8 bits once. But again, the code which takes sigma to the k to sigma to the k to the symbol sigma to the k, the rate is 1.
No, because if you say that we're going to calculate the rate here over 3n.
Yes, but same here. Here?
Oh, I see.
Yeah. But it's not, the reason it's not fair when distance is 1 because different things go to different things, and that, and there is one index, and the rate is 1. But it's not fair because, I mean, yeah. I mean, there is a real reason. Like, when you talk about distance, you say how many things you're allowed to change. And when you take these in like triplets, then you are essentially saying that if you change 1 or 2 or 3, it counts as 1. That's kind of unfair. But you know, as long as it's not, as long as it's moderate, then you can fix it. So it's still not okay, but you can fix it. That you cannot fix it.
So
One symbol.
Yeah, so you just don't. Yeah.
Right. So that's like the cheating.
That's shouldn't be.
If you do the clear.
Yeah.
No, but then, good, yes. But then I won't be able to analyze. Because now, okay. That's a great question. So let me just, so if I think of it as FQ to the 3n, that, right? Then when I'm going to argue about the distance, here, when I have a 0 symbol, I know that all of them are 0. Here, it could be that this is 0 and this is not. Okay? So the fact that they're kind of bundled together is crucial. Good. So it's a cheat in that sense, because I'm kind of saying I know something about the pattern of zeros when viewed like that. But when viewed like that, it's okay, and you can fix it. Yes, but it's still okay. I mean, even as like that, it's not like a trivial thing to do. Okay, so let's analyze that. So I mean, actually, there is the distance analysis. So let's try to do that. But there is a problem already at the get going because we need. So what do we need? Like, what did we use before? Schwarz-Zippel. The zeros, the bound on zeros according to Schwarz-Zippel, which told us that. So let me write it a bit differently. It told us that for any degree at most t, again total degree almost polynomial. So I wrote before I wrote that the number of zeros in FQ over FQ is most t times q, but let me write it differently just so I can. So let's go over all p's in FQ over FQ times FQ, all points, and I'm going to have an indicator. This is a 1 or 0 depending on whether this holds, and this is f of p is 0. And so this sum counts the number of zeros of f of the plane. And Schwarz-Zippel told us this is most t times q. Okay. And now we're going to use an extension of it. It's less trivial to prove. It's not trivial to prove. In which you can actually get the same bound on something potentially larger with a stronger statement. So it will replace that by the multiplicity of f at p, hence the name multiplicity. So multiplicity of f at p is, it's a number, it's an integer that tells you what is the, and you need to define it appropriately, but what is the, how many times f vanishes at p? F vanishes, f is 0 at p. So for example, if f is not 0 at p, it's 0. If it's 0 at p, it's at least 1. But maybe f and its derivatives, think of one univariate case, is 0. So that would be 2, and so forth. So that's the. So this is, in our case, I only care about 0, 1, or 2, but generally this tells you need to formally define it, how many times f vanishes. The right way to do it is with the derivatives, and in fact, the right way to do it is with what's called Hasse derivatives. But never mind that. It's not going to be important to us, especially because you're only using it for 0, 1, or 2, and then Hasse and usual derivatives are the same. But there is an asterisk in what I'm saying there. This is not really formally defined because I need to find out multiplicity is. But for us, multiplicity will be 0, 1, or 2, and it's going to be 2 when f as well as its two derivatives are 0, which is the kind of makes sense. No, because right, so you check two-dimensional. So if you want the derivative to be 0, you have to have it in all directions. I'm doing like that, but it's not continuous flow. I don't know how FQ looks like. Okay, so good. So, but for us, the only thing you really need to take from this is that. So again, we want to analyze distance. So whenever a symbol is a 0 symbol as a triplet, then we know that it contributes 2 to this sum. That's the point. Right? So the number, for example, the number of zeros is most TQ over 2. Number of zeros, I think one message, I'm not comparing it anymore. One of the 0 message, but it's the same thing. And now I'm saying how many 0 triplets could be. So every such 0 triplet, say P1, adds 2 to this sum. And so the number of zeros is most TQ over 2, because each of them contributes 2.
Can you repeat again why is it only 0, 1, 2 and then
Yes, because no, I mean it could be the case that f vanishes even more on B, but I'm saying that if you look at for the analysis, if you look at a 0 symbol, And what does it mean? It means that at that point, P1, f vanishes and its two derivatives, which means that this thing is at least 2. Or I should have said at least. Because the definition of this, if you probably define it, it counts the depth of derivatives, all of which vanish.
Isn't it one? Because
So this is 1. When f vanishes, it's 1.
Oh, so we start from
It's not from, yeah, exactly.
So it's like 1 and then 2.
Right. Because 0 also makes sense. 0, it means that it's not 0. Like 0 means which f of p is non-zero. So when this is 0, it means that f of b is 0. When this is not 0, it means that it's not 0. But this holds more information than just whether f is 0 or, I should say, vanish. It's vanish in p or not. Right? Because if I tell you that, I mean, for example, take this function. So you know, over the years, depending on the is but you know that this vanish, you know that this has like 3 zeros at 0. But the reason there are ways of thinking about it, but the reason you know is because the derivatives also vanish. Now, if you have 2 variables, so you know that this has like 2 zeros at 0, and so forth. Because of this. Okay, but anyhow, so any 0 symbol contributes to this point, and summing 2s, one is more sticky. Summing this number of 2s, then another more sticky than this one. Good, and now it's just a matter of so the distance is n minus the number of 0. Oh, it is. You can take it in most cases, which is this n minus tq over 2. And n is q squared, just remember that. And this is q squared, as before. So this is q minus 2 over 2. Okay. What's the rate? Oh. So maybe I should just say this is good. Before, I don't know if you remember, we don't remember. After you see it was q times q minus t. Now it's q times q minus t over 2. You lose less. It's good. But you know that in the rate you're going to get something worse because there is a 3 here. So you really want the 2 to be better than the 3. 2 doesn't sound better than 3, but it's going to be squared. So let's do the rate. Or maybe just summarize the distance, the relative distance, and dividing by q squared. So this q goes away. We get 1 minus t over q. Just make it the normalized version. And now the rate is k over n. K is as before. 2 squared 2. It's the same. Sorry. The 3n, which is is t squared over 2 divided by 3 times n, which is q squared. So this is q squared. The tangent, you see the square coming? So this is 1/6 t over u squared. 1/6 is there. I don't think it's 2/3. No. Oh, then that would be there. Yeah, maybe it's better than this. So that's better. Before it was 1/3, 1/2. Oh, now it's 1/6. But look at that. T over Q is twice. T over Q is twice minus that. So the 2 is going to be squared. So it's like 1/6, 1 minus delta squared.
No, it's actually.
Which is exactly, it's like 2/3. The 2 is squared. You pay the 3, you gain a 2, that's 12. It's good. It doesn't seem open, but that's 2/4 is better than 1. You want it to be that. Good.
So it means we can use the same method like with assuming the like a variables, like
Yes.
the derivatives, and then get better.
Yes. Right, so you get better. This will get closer and closer to 1, because this will be a lower bad number, this will be a better number, and this will be 3 now. So it's even better. So this will go to 1, which is good. But the symbol size is also going to get very large. Like now it's FQ 3 times, but next time it's going to be, you need to take all the 2 directional derivatives. And it kind of goes exponentially fast. And then the cheat is significant because you are putting a very large symbols. You need to reduce them back, otherwise you're cheating. It's not the code say. And then you're going to pay something, and overall this gives you something which is very good. I mean, you begin here, you pay there, and overall it's really good. It's not close to Gilbert-Varshamov or anything like that, but it's really good. Maybe I can say not exactly. That's what it is. So now what I try to exemplify here, again, we don't care about the code themselves, is that, I don't know, it's kind of cool that, you use more, it's like, it's not really a use of polynomial, it's like a forced appearance of a Taylor expansion here. Like you look at the function as a function. For example, by the way, if you look at it for a second, I'm not sure I'm correct, but let's see, the degree T, let me check, what's the degree? Is T, which is, where is the case code? It's twice, it's, okay, it's, I don't really care about the 2, but let's just write it. Like that's the degree, right? And K is, with respect to Q, and K could be very close to N. Yes, K could be very, I mean, if you think of K, which is really good, you can get K closer and closer to N. So when you get something that's, maybe I'm wrong here, but when you get closer and closer to N, I mean, you can get it as far as you want here if you want. Maybe I'm wrong. Because of that. Okay, now. What I'm trying to say is that this could be larger than Q. Because N is Q, scope of N is Q. This could be larger than Q, I think. And then when you look at it, you think, I cheated. No way. Something is definitely wrong here. It's not wrong, but it's wrong. Simply wrong because how can I look at degrees on polynomials whose degree is larger than the field size? It doesn't make sense. Because, for example, x to the q is x in the field size q. So these two distinct polynomials that are the same when you have as functions, they are the same. But as polynomial, but as the polynomial, they are different. So this is like a ring of a bell, like a little. I mean, it shouldn't be a code should definitely be bijective, very different. But the point is, we didn't see these functions. We didn't analyze them thinking as polynomial, but also as functions when we look at the first Taylor expansion. So for example, if you take the derivatives of that, you get qx to the q minus 1, which is what? 0, right? Because q is 0, and this is 1. When you derive it. So as polynomials, they are the same. But as functions, if you take more information from them, they are different. And this is what kind of happens here. You use more information than just a polynomial. What they do is what is mapping to as polynomials.
As functions,
Yes, the functions they are the same as polynomials, but identical.
No, so
like
as
Taylor, we got
no,
Taylor because you
as functions,
Over
they are not the
Q.
same.
Over
Yeah.
Q. they are the same.
evaluate them.
But
When you're taking
but
the
you can do
derivative,
more.
taking it in the direction of the partial derivative and not the analytical derivative.
Okay,
It's
so,
like informal derivative. It's not the derivative of the function.
okay, so let's see what we agree about. I think we don't agree about
Maybe mapping.
what we said. Yeah. So do you agree that these are not the same polynomials? And if I only evaluate these things, I get always the same thing. And if I derive them, I don't get the same.
Well,
Informal derivative.
Right, and then evaluate that. Okay, so what we are agreeing on, I probably said something about this, just want to figure out. What we agree on is that if I only evaluate this thing, I cannot distinguish it from that. But if I also evaluate derivatives, I can. So this for me is a function. Maybe it's
but
It's not the analytical derivative. That's the problem. Since it's not the analytical derivative, that's not the real derivative of FQ.
it is a real derivative, not
No.
real.
The formal derivative is not the analytical one over fields but their characteristic is not zero.
The first one is, by the way, you need to talk about asset derivatives. Okay. So
it's just function is defined by the mapping. The mapping is the function.
for me, the function is not just the number. Right, no, I agree, I understand. The function is like, okay. So for example, these are two things that when you evaluate them, you can distinguish them, but when you do something other than evaluating them, which I think I consider still as part of their functionality. Okay, what's the definition of a function? Yeah, if you think a function as just evaluate it, then I'm wrong. But if you think a function as do things to it, like essentially you apply operators here, and okay, I understand. So if you have things and you apply these n operators on them, that's what I'm doing here. But should I call it a function of the thing?
It's just the thing machinery that allows you to distinct the polynomial.
Right.
The function.
Yes.
It's the other way around.
Okay. So okay, it's fine. Yeah. I'm okay with the gap. So let me in the last couple of minutes say something informal about this. Okay, the last thing. And then we'll meet again. So this doesn't really scale. I mean, it's okay, but there are problems with this construction, and it also gets kind of ugly. It's better to have nicer construction. And the last couple of minutes say something informal about this. Okay, the last thing. And then we'll meet again. So this doesn't really scale. I mean, it's okay, but there are problems with this construction, and it also gets kind of ugly. It's better to have nicer construction. And there is like a cool construction. Right, so, and because of that, I kind of have the other notion of function. It's fine. So it kind of seems that what's the problem with Reed-Muller? You decrease the field size because you look at the higher dimension, so the coupling between Q and N is getting better and better, but you're evaluating many points. Q, and so forth. And it already initially feels like it's kind of it's too much because, so for example, if you have a degree D polynomial and you evaluate on the plane, then you can skip a few points because you can anyhow kind of reconstruct them at the other points. But there are dependencies. That's kind of Reed Solomon. There are dependencies between things. So taking the whole plane is easy because you can use multiple, but maybe there is a better choice within the plane that does as well and doesn't scale so horribly. And there is one. So for example, just for fun, if you look at so let's keep our idea of evaluating polynomials in two variables, But let's not evaluate them on the plane. Well, let's evaluate them on a subset of the plane. And it's going to be what's you can kind of slightly inform the variety of algebraic curve. And for example, let's consider the curve. Let's call it C. Let's see. It's a curve. What can I do? C curve CU. Say you take all xy's in FQ squared, but not all of them. Just maybe say some that satisfy some polynomial relation that you can argue about. So a good one, a great one, but a good one would be, and that's the point I said I'm going to use Q, which is none of time. So I'm going to assume that Q is P squared. P will be a high power, but I need Q to be a square of, like an even power of prime. But just only way, only reason I'm going to do it. So this is called like the Hermitian curve. If you stare at it for a second and you know things about this, and this is the place and this is the norm of it. And this is the curve, so it's not everything here. But it's a lot. You can actually show it's not trivial. That there are at least, I mean, there are most Q squared things there, which is P to the fourth. But you can actually get like PQ. That's one. So it's a big chunk of the plane. And we're actually going to do that sometime. We're going to analyze this. But turns out that evaluating now bivariate polynomial only on this curve carefully is a better idea than evaluating on the entire curve. What I mean carefully I mean that some things, that's why I was so pedantic about that, and I understand the discipline. Some polynomials may be different polynomials, but they be the same as functions mappings on the curve. For example, these two. These two functions are the same on the curve, but they are different. So you need to be careful about how you count the degrees of freedom of functions that you have, because you don't have all functions that you may write. Some of them may be the same as functions. But it turns out that you can actually find a space of a vector space of bivariate polynomials. The name for it is a Riemann-Roch space. Anyhow, but it turns out that this actually is not the greatest suggestion. The greatest, our greatest, not the, our better suggestion is to take a tweak of this construct, of this curve. It already looks weird because you never see these. So the randomness of it, you don't divide. You only multiply and add and subtract. So when you do this, immediately you are where it is defined in some question. So let's consider all points xy that satisfy that. You also have roughly PQ solutions, by the way. It's harder to see each. But I want to have many points. So what we're going to do, I'm going to take still a one-dimensional thing at all, but in higher dimensions. Say in 3 dimensions, I'm going to look at all x, y, z, such that the same equation is satisfied with neighboring indices, So for x and y and z and w, and so forth. So say I'm looking at, so for example here, I'm looking at all points x, y, z that satisfies these two equations. So it's something that lives in 3D, but it's like a one-dimensional instance, because you have two constraints. If it was like linear, then it would be 2 dimensions, but you have one, so it's a line in the. So that's like a curve in 3 dimensions. And actually, if you keep doing that, you need something like Clovian dimensions to get endpoints. Then what you would get is something amazing. You would get a code called Algebraic-Geometric code that beats the Gilbert-Varshamov. So there are codes. Actually, this is the points on which you evaluate, and I need to tell you what the functions are, but that requires like a full year course. And I gave it one semester, so you can actually show that you can get over delta to be not 1 over log Q, but actually square root. That's exponentially better dependent. So maybe we'll end like that. But this is a fascinating example of a very deep mathematics. It's fact code that actually do better than the it does better only when Q is at least 49 or something. Yeah. There's a constant in low Q, which I know. But okay, so I'm not going to talk much about that at all about that. I just wanted to say it as one example.